Electrical engineering exam questions. Hello everyone, welcome to my channel. In this video, we're going to solve together 15 questions that frequently appear in electrical engineering exams. The topic of this video is the linear circuits. Let's go to the first question. For the circuit of the figure, E is 5 volts. IA is 3 amps and IB is 2 amps. If R1, R2 and R3 are all equal to 1 ohm, calculate I1, I2 and I3. Okay? This is the exercise. Let's go to the solution. To facilitate our calculation, we're going to use some labels here. We're going to label this node V1, we're going to label this node V2, and the current that flows here, we're going to label it as I4. Alright? And to calculate what's being asked, we are going to apply the nodal rule at nodes V1 and V2. What does it mean? The currents that enter node V1, IA and I4, have to be equal to the currents that leave the node, I1 and I3. Okay? So, IA plus I4 have to be equal to I3 plus I1. The same is going to be done for V2. I3 enter the node, and what are the currents that leave the node? I4, IB and I2. So I3 is equal to I2 plus I4 plus IB, okay? We have written this in terms of current. Now we are going to try to write this in terms of voltage drops and resistances as the following. IA is 3 amps. 3 amps plus I4, we are going to leave it the way it is. I3 is equal to V1 minus V2 divided by 1 ohms. Plus I1. I1 is V1, the voltage at the node, divided by the resistance, 1 ohm. Okay? Now we are going to do the same for the second equation. I3 is V1 minus V2 divided by 1 ohm. Which is going to be equal to I2. I2 is the division between the voltage at the node by the resistance. V2 over 1 ohm plus I4, we are going to leave it the way it is, plus IB. IB is 2 amperes. Alright? We have one here, we have one here, 1. We don't have to worry about it. Okay, it's a simple division. And we get that this becomes this. 3 amperes plus I4 equal to V1 minus V2 is E. Okay? V1 minus V2 is E. E is 5 volts. So 5 volts divided by 1 ohm is 5 amperes. Plus V1 divided by 1 ohm is simply V1. And for the second equation, we know already that this is 5 equal to V2 divided by 1 is simply V2 plus I4 plus 2 amperes. Okay? We are working with this system of equations. And if we equate this, we are going to discover that I4 is buff. I4 is buff V1 plus 2 amperes, and I4 is equal to 3 amperes minus V2, okay? We are going to solve this, and we are going to discover that V1 plus V2 is equal to 1 volts, okay? This is what we can infer from this, all right? And since the exercise gave us that V1 minus V2 is equal to E, which is equal to 5 volts, and we already know that V1 plus V2 is equal to 1 volt, we discover that V1 is equal to 3 volts. Okay? V1 is equal to 3 volts. And V2 is equal to negative 2 volts. Okay? V2 is equal to negative 2 volts. Alright? V1 minus V2 is equal to 5. Okay? 3 minus 2 is equal to 5. Okay? You invert the sign here. And since I1 is equal to V1, 3 volts, divided by 1 ohm, we know that I1 is 3 amperes. I2 can be calculated in the same way. I2 is V2, negative 2 volts, divided by 1 ohm, which is negative 2 amps. Okay? We've discovered that I2 is negative 2 amps. What does it mean? It means that instead, when we find a negative sign, it is not wrong. What does it mean? It means that instead of going downwards, actually, the current is going upwards here. And finally, I3 is equal to E divided by 1 ohm. Okay, we already know that I3 is then equal to 5 amperes. Okay, so my friends, these are the results. Okay, these are the results of the first exercise. Let's go now to the second exercise. Question 2. For the circuit of the figure, calculate the maximum power that can be delivered to the load. Okay, my friends, this is the question. Let's go to the solution. The first thing that we need to understand here is that for maximum power transfer, the impedance of the load has to be equal to the complex conjugate of the impedance of the circuit. As we work in here with only resistive elements, for maximum power transfer, the resistance of the load has to be equal to the resistance of the circuit. This is our first conclusion. Okay? And how do we get this? The equivalent resistance. To find the equivalent resistance, we are going to use Thevenin's equivalent circuit. Okay? And to come up with Thevenin's equivalent circuit, we have to calculate the open circuit voltage. Okay? we are going to open the circuit here, and we are going to calculate the open circuit voltage. Okay? And we are going to use the following currents and voltages. We're going to call this current I1. This is going to be I2. This node is E1. This node is E2, and this current here, I4. Notice that we are going to open the circuit here. So I4 we already know is equal to 0. Okay? And further, we are going to apply the nodal rule at nodes E1 and E2. For node E1, the currents that enter the node E1, here there is an additional current here, I3. Okay, I1 enter the node, and I2 and I3 leave the node. Okay, I1 is equal to I2 plus I3. Developing this, we get that I1 is 24 volts minus E1 over 3 ohms. Okay? This is I1. Now let's go and describe I2. I2 is E1 over 6 ohms. And the other current is I3. I3 is E1 minus E2 divided by 2 ohms. Okay? This is the equation for node E1. Now let's do the same for node E2. What are the currents that enter node E2? I3 and 1 ampere. And what are the currents that leave node E1? Only I4, and we already know that I4 is equal to 0. Then it is going to be equal to 0. And from this, we discovered that I3 is equal to negative 1 amp. Negative 1 amp. But I3, as we can describe, I3 can be described as E1 minus E2 divided by 2 ohms, which is equal to negative 1 amperes. And from this, we discovered that E2 is equal to E1 plus 2 volts. We are going to use this to calculate the other quantities. If we return to the first equation, and using this, we're going to get that E1 is equal to 18 volts, and only summing, we discovered that E2 is equal to 20 volts. Okay? E2 is equal to 20 volts, and E2 is equal to the open circuit voltage, the voltage here, because there is no voltage drop here. The current is 0. Therefore, VOC is equal to 20 volts. All right. With these values, we can calculate the maximum power, but this is only the first step. We need to find the equivalent resistance. To calculate the equivalent resistance, we put the sources at rest. A voltage source at rest is a short circuit, and a current source at rest is an open circuit. This is what we are going to do here, and we are going to use this circuit here. Okay, we have here 1 ohm, we have here 2 ohms, here 3 ohms, and here 6 ohms. Okay, the parallel connection between 6 ohms and 3 ohms is 2 ohms. We have 2 ohms here, 2 ohms here, in series with 2 ohms and 1 ohm, which is 5 ohms. Then this equivalent resistance here is 5 ohms. We've calculated the parameters of Thevenin's equivalent circuit. Then the circuit is going to be the load the equivalent resistance in series and the open circuit voltage. Okay? We already know that here is also 5 ohms. Okay? We talked about this in the beginning of the video. And the maximum power delivered to the load is going to be 20 volts divided by 10 ohms squared. Okay? The current here is 20 volts divided by 10 ohms. And to calculate the power, we have to square it times the resistance. And this is going to be equal to 20 watts. Okay? This is the maximum power that can be delivered to the load. The maximum power occurs when the resistance of the load is 5 ohms. And this maximum power, its value is 20 watts. Okay, my friends, this is all for exercise 3. Let's go exercise 2. Let's go to exercise 3. Question 3. A source generates the periodic signal of the figure, which represents the electrical current that passes through the load. If the source delivers 80 joules per period to the load, calculate the RMS and the maximum value of the current. Okay, my friends, this is question 3. Let's go to the solution. The first step to calculate what the exercise requested will be to understand the period of this signal. Observe that from here to here it's 6.6 seconds, and from here to here 0.9 seconds. We are going to do the following. We're going to call here X, X, and X. Okay? Then 3 times X plus 2 times 0.9 is equal to 6.6 seconds. Okay? By developing this, we find that x is equal to 1.6 seconds. Okay? And the period of the signal is then the period is equal to 1.6 seconds plus 0.9 seconds, which is 2.5 seconds. Okay? This is the period of the signal here. We are going to use this to calculate the power. The energy per period delivered to the load is 80 joules, which is equal to power times the period. Okay? Which is P times 2.5 seconds. And using this expression, we find that the power is equal to 32 watts. Alright? We use the power to find the RMS value of the current. Okay? The RMS value of the current can be found as P is equal to I squared times R. Okay? Where P is 32 watts, I squared times R, which is 2 ohms, and then we find that the RMS value is equal to 4 amperes or 4 amps. Okay, so we know this. Now what we need to do is to calculate the maximum value of the current. I'm going to erase it here to get some room. To calculate the maximum value of the current, we use the RMS value of the current. The RMS value of the current can also be calculated by integrating from 0 to 1.6 and from 1.6 to 2.5. So we're going to use this. Okay? This is how we calculate the RMS value of the current. The period is 2.5. And you see that there is value for current only from here to here. And here, the current is 0. Then we are going to split this in 2. It's going to be since the signal is 0 here, we do not need to worry about it. Okay? And this is equal to 4. Alright? Then 1 over 2.5 is equal to 16. Okay, we pass the root to the other side, and then it becomes 4 squared, which is 16. And we get that from 0 to 1.6, I of t squared dt is equal to 40. Okay? Since the current is constant here, it does not change. From 0 to 1.6, we can pass this to the other side. Okay, and here 0, 1.6. And by developing this, we get that and in this way we find that the current is equal to 5 amperes. Alright? Then the maximum value of the current is 5 amperes and the RMS value of this current is 4 amperes. This is what exercise 3 requested of us, and we've just calculated it. This is all for exercise 3. Let's go to exercise 4. Let's go to exercise 4. Consider the circuit of the figure. The exercise asks us, what is the value read by the voltmeter? Okay? The voltmeter is here, and the exercise wants us to discover the reading of the voltmeter. How do we calculate this? How do we discover the value read by the voltmeter? The circuit looks complex, isn't it? But there is a catch here. Take a look at this capacitor and this inductor. The capacitive reactance is equal to the negative of the inductive reactance. What does it mean? It means that the voltage across the capacitor is the negative of the voltage across the inductor. Okay? Therefore, they place together like this in a circuit causes a short circuit. Okay? The voltage drops here cancel each other out, and there is a short circuit here. You may not notice it beforehand, but upon inspecting the circuit, you're going to discover that there is a short circuit there. And then the circuit becomes okay? No current is going to flow here to this resistor and there to this branch. No, all the current is going to flow straight here, passing through the short circuit. Then the current is going to be 20 volts divided by 2 ohms, which is equal to 10 amperes. The current that flows here is 10 amperes. Therefore, the voltage across this inductor here is going to be 10 amperes times J4, which is equal to 40 phase 90 degrees. Okay? And the voltage, the exercise, I didn't ask for this, but we can say that the voltage across the capacitor is the negative of this, which is 40 phase negative 90 degrees volts. And together they are equal to 0. VL plus VC are equal to 0, which is 40 phase 90 degrees plus 40 phase negative 90 degrees, which is equal to 0, okay? Because of the short circuit here. Whenever we have a branch like this, with the magnitude of the capacitor impedance equal to the magnitude of the inductor impedance, we have to pay attention because there exists a short circuit in the circuit, okay? So this is the voltmeter reading. It is going to read 40 volts. Alright, my friends, this is all for exercise 4. Let's go to exercise 5. Now let's go to exercise 5. For the circuit of the figure, what is the value of the capacitive reactance for maximum power transfer? Okay, my friends, this is the exercise. Let's go to the solution. How do we calculate the maximum power transfer? For maximum power transfer, the impedance of the load has to be equal to the complex conjugate of the impedance of the circuit. The impedance of the circuit is okay? The impedance of the load for maximum power transfer has to be equal to the complex conjugate of the impedance of the circuit. Alright? And here at the load, we have a series connection between these two elements, and they together are in parallel with this capacitor here. Okay? Then we are going to have this negative JXC in parallel with 10 plus J40. Alright? This is what we need to understand before calculating anything. Let's inspect the angle here. We are not going to work with the magnitude. The catch here, the trick, is to work with the angle. Let's understand the angle of the load. The angle of the load is going to be the inverse tangent of negative 75 divided by 45. And this angle here is negative 59 degrees. Okay? And we are going to now make this angle be equal to the angle of this expression here. Okay? Negative JXC in parallel with 10 plus J40 is equal to 40 XC minus J 10 XC divided by 10 minus J XC minus 40. All right? The parallel connection becomes this. What we need to do is to assess, I'm going to call here 1, and we need to assess the angles. There will be an angle here, we're going to call it phi 2, and there will be an angle here, we're going to call it phi 3. We're going to assess the angles and see how they match with this angle here. All right? So this is exactly what we are going to do. I'm going to erase here for some room. Just wait a minute. The angle, I'm going to write it again. The angle of the numerator is phi 2 is going to be equal to the inverse tangent of negative 10 XC divided by 40 XC, okay? And this angle is equal to, I cut this with this, the angle is equal to negative 14 degrees. Now let's do the same for the denominator. The denominator here, phi 3 is equal to the inverse tangent of the negative of the inverse tangent of XC minus 40 divided by 10, okay? And okay, this is the angle. All right? Then we conclude that phi 1 is equal to phi 2 minus phi 3. Okay? We can pass this signal to the other side. It becomes this. Okay? Negative phi 3 here, negative phi 3. So it's going to then be equal to negative 59 degrees equal to negative 14 degrees plus the inverse tangent of XC minus 40 divided by 10. All right? This is how we are solving this problem. Of course, there may be other ways of solving this problem. This is the way we've chosen to follow. Okay? So the inverse, I pass this to this side. So the inverse tangent of XC minus 40 divided by 10 is equal to negative 45 degrees. And since the tangent of negative 45 degrees is negative 1, we know that XC minus 40 divided by 10 is equal to negative 1. And then we discovered that XC is equal to 30. All right? Then the impedance here is going to be J negative 30 ohms. Okay? So this is the value of the capacitive reactance for maximum power transfer from the source to this load element. Okay, my friends, this is all for exercise 5. Let's go to exercise 6. Question number 6. In a circuit, a source feeds a load for a long time after reaching steady state, when suddenly the switch changes position from A to B, thus isolating the source from the circuit. Under these new conditions, calculate the initial value of the capacitor voltage and the expression of the capacitor voltage for all t after switching. Okay, my friends, this is the question. Let's go to the solution. Before switching, the circuit is this. In steady state, the capacitor acquires the voltage of the source. Then, immediately after switching, Vc is equal to 10 volts. Okay? When the switch changes position from A to B, the circuit becomes this. And the capacitor discharges through the resistors. Okay? This is a circuit for a capacitor discharge. And the circuit becomes okay? It is possible to notice that there's going to be a current here and a voltage drop here. Okay? V of t, or the capacitor voltage, over R, okay, plus C, the derivative of the capacitor voltage with respect to time, has to be equal to 0, okay? This is the differential equation that we are going to work with. The capacitor voltage is here, okay? The capacitor voltage is here. Capacitor voltage divided by the resistance is equal to the current, here, plus this voltage here, the derivative of the voltage with respect to time, with C as the constant. This has to be equal to 0. And the solution of this differential equation is and I know that R is equal to 5 and C is equal to a fifth, which is 1. Then the expression for all t of the capacitor voltage is equal to this. Okay? Alright, my friends. This is the solution of this question number 6. And I don't know if you understood it all here, but current, voltage over resistance, and the current that lives here, okay, is the derivative of the voltage with respect to time, with C as the constant, and the current that goes up here plus the current that goes down there has to be equal to 0. Okay, one more time. The current that goes up here plus the current that goes down here has to be equal to 0. And this is the rationale behind our expression. Okay, this is all for exercise 6. Let's go then to exercise 7. Question 7. It is wished to connect a load at points A and B of the circuit. The exercise wants us to calculate the value of the impedance of the load for maximum power transfer. Okay, my friends, this is the question. Let's go to the solution. For maximum power transfer, the impedance of the load has to be the complex conjugate of the impedance of the circuit. How do we calculate the impedance of the circuit? It is easy. We simply set the forcing elements, the sources, at rest. A voltage source at rest is a short circuit, and then a current source at rest is an open circuit. And observe that they have the same frequency, 2 and 2. Therefore, the reactance here is going to be, let's calculate it. The inductive reactance is JWL, which is equal to J2. Okay? We're going to use it. Then we have a circuit like this. We want to measure the impedance at points A and B. Observe that these two impedances here, the resistance and the reactance, are in parallel. Then I'm going to call it Z1. It's going to be the parallel connection between J2 and 2 ohms, which is J4 over 2 plus J2. Okay? And they will be like this. They are in parallel to each other, but they are in series with this 3 ohm resistor. Then Z total will be J4 over 2 plus J2 plus 3, and this is J4 plus 6 plus J6 over 2 plus J2, which results in 4 plus J. So this is the equivalent impedance of the circuit. And now we can respond to the question, what is the value of the impedance of the load for maximum power transfer? For maximum power transfer, the impedance of the load has to be the complex conjugate of the impedance. Then Z load minus J. Okay? This is the impedance of the load for maximum power transfer. Okay, my friends, this is all for exercise 7. Let's go to question 8. Question number 8. Two single-phase synchronous generators are connected together in parallel, as shown in the figure. The exercise wants us to calculate the magnitude of the current flowing between them. Okay, my friends, this is the question. Let's go to the solution. We are going to apply KVL to calculate the magnitude of the current. Okay, so 3,500 phase 0 degrees volts is going to be equal to the voltage drop here plus the voltage drop here plus this voltage here. I'm going to bundle these two together, and it's going to be J60 times the current plus 3,500 phase negative 40 degrees. Okay? And if we solve for I, we get that I is going to be equal to 3,500 phase 0 degrees minus 3,500 phase negative 40 degrees divided by J60. J60 is written there in the Cartesian form. We can also write it in the polar form. And in the polar form, it becomes 60 phase 90 degrees. And when we solve this, we get that the current is equal to 40 phase negative 2.7 degrees amperes. Okay? And the answer is, the response of this question is 40 amps. Okay? This is the response. Alright, my friends, very easy, isn't it? This is all for exercise 8. Let's go to exercise 9. Question number 9. For the circuit of the figure, calculate the average power consumed by the resistor R. Okay, my friends, this is the question. Let's go to the solution. How do we calculate the average power consumed by the resistor? We're going to apply superposition. Why superposition is necessary? Because the frequencies of the sources are different. Okay? At first, we are going to put the voltage source at rest. A voltage source at rest is a short circuit. Okay? Then the circuit is going to become okay? There is a parallel connection between these two resistor here, and you know that they equal. They equal. Can you see they're equal? And here is 1 amperes. If they equal, then this current is going to split equally between them. 0.5 here and 0.5 here. Okay? Then, when the forcing term is only this current source, the power, we're going to call it P1, is 0.5 amps squared times the value of the resistance. And this is equal to 1 watt. Okay? Easy, easy. Now, let's do the same. Now, putting this current source at rest. A current source at rest is an open circuit. Okay? Then the circuit is open here, and we have this. Okay, there is going to be a current flowing here. Alright, and the magnitude of the current is going to be 1 ampere or 1 amp phase 0 degrees. Okay? And the power, I call it P2, is the current squared times the resistance, and it is 1 squared times 4, which is 4 watts. And the average power consumed by this resistor here is going to be P1 plus P2, which is 1 watt plus 4 watt, which is 5 watts. Okay? This is the response of exercise 9. Let's go now to exercise 10. Question number 10. For the circuit of the figure, find the Thevenin's equivalent resistance seen from terminals A and B. Okay, my friends, let's go to the solution. To find the Thevenin's equivalent resistance, we put the forcing terms, that is, the sources at rest. A voltage source at rest is a short circuit, and a current source at rest is an open circuit. This is what we are going to do. Okay? A and B. We have a series connection here between these two elements, and we have a series connection here between these two elements. Further reducing the circuit, we arrive at and now we have the parallel connection between this resistor and this resistor here. Okay? Therefore, this is the value of Thevenin's equivalent resistance as seen from terminals A and B. Okay, my friends, this is all for exercise 10. Let's go to exercise 11. Question 11. For the electrical circuit of the figure, calculate the electrical current that flows through the 60 ohms resistor immediately after the switch is closed, and the current that flows through the 26 ohms resistor after steady state is reached. Okay, my friends, this is the question. Let's go to the solution. At t equal to 0, immediately after the switch is closed, the capacitor behaves as a short circuit. Okay? Then this current here, I is equal to I1 plus I2. Alright? Applying the nodal rule at node E1, we obtain 90 volts minus E1 over 10 ohms, okay? This voltage here minus this voltage here divided by this resistance is this current here. As the capacitor is behaving as a short circuit, the current I1 is going to be E1 over 60 ohms. And the current I2 can be found by applying resistance reduction here. The parallel connection between 8 and 8 is 4. Okay? 4 plus 26 is 30. Alright? In this way, we find the value of E1, the voltage at this node here, which is 60 volts. Okay? And the value of the current I1, which passes through this resistance here, at t equal to 0, immediately after switching, is going to be 1 amp or 1 ampere. This is the first result. Let's go to the second, to letter B. Let's raise here. What do we want in letter B? We want the current in steady state. Okay? In steady state, the capacitor opens. It's an open circuit here. Okay? So no current flows here in steady state. The capacitor behaves as an open circuit. Then we're going to have a circuit like this. And I is equal to 90 volts divided by 40 ohms, which is equal to 2.25 amps or 2.25 amperes. Okay, my friends? Do you fully comprehend? Okay? This is all for exercise 11. Let's go to exercise 12. Question 12. The circuit of the figure is composed of a sinusoidal voltage source, a resistor, a capacitor, and an inductor. Knowing that the power supply has an RMS voltage of 90 volts and that R, XC, and XL are all equal to 10 ohms, calculate the power in watts involved in this circuit. Okay, my friends, This is the question. Let's go to the solution. The exercise wants us to calculate the power in watts involved in this circuit. To calculate the power, let's first calculate the current. Okay? And use these values here. The total impedance, or the equivalent impedance, is going to be 10 ohms for the resistor, negative J10 ohms for the capacitor, and positive J10 ohms for the inductor. Okay? Observe that when put in this way, the inductor and the capacitor cancel each other out. Then the equivalent resistance or the equivalent impedance is 10 ohms. With this result, we can calculate the current phasor, which is going to be 90 phase 0 degrees volts divided by 10 ohms, which is equal to 9 phase 0 degrees amps, or 9 phase 0 degrees amperes. Okay? With the current, we can calculate the magnitude of the power in watts. The power in watts is the real power. And we see that when there is only the resistive elements, we saw that in this way the reactances cancel each other out. We're going to see that the apparent power, the magnitude of the complex power, the apparent power, is equal to the real power. When this happens, we can calculate it in this way. It's going to be the current squared times the resistance, which is equal to 9 squared times 10 ohms, and this is 810 watts. Okay, my friends, this is how we calculated the power in this circuit. Alright, this is all for exercise 12. Let's go to exercise 13. Question 13. Calculate the average power in watts consumed by the 5 ohms resistor if the given value of the AC source is the RMS value of the current. Okay, my friends, let's go to the solution. Watch out! There is a trick here. Not until you understand that the current of the current source is the only one that flows through the branch it is connected, you will visualize the solution. What does it mean? Regardless of this voltage source here, the current of the current source is the only one that flows here. Okay? No other current goes there. The only current that flows in this branch here is the current of the current source. Okay? When you understand this, you're going to see that the power is simply I squared times the resistance. The exercise said that this value here, 10, is the RMS value. And whenever calculating power, we have to use the RMS value, not the peak value of the sinusoidal. Then the power is going to be 10 amps squared times 5 ohms, and this is 500 watts. Okay, my friends? This is the result of this question. Very easy, isn't it? But sometimes it can be difficult because some people may not visualize this property that the current of the current source is the only one that flows here. Some people may apply the nodal rule here to try to find the currents flowing here. And in this way, you may make a mistake attempting to solve this exercise. All right, my friends, this is all for question 3. Let's go to question 14. Question 14. In the circuit of the board, calculate the impedance of the load so that maximum power transfer occurs. Okay, my friends, this is the question. Let's go to the solution. For maximum power transfer, the load impedance must be the complex conjugate of Thevenin's equivalent impedance. What does it mean? The load impedance must be the complex conjugate of the circuit's impedance. And the circuit's impedance can be found by using Thevenin's equivalent circuit. All right? This is what we are going to do. To calculate the equivalent impedance, we set the voltage source at rest. A voltage source at rest is a short circuit. And we are going to open the circuit at these terminals here to calculate the equivalent impedance. Okay, and then the circuit is going to become observe that the frequency here is 4. Then the value of the capacitive reactance is going to be negative J ohms. Okay? Firstly, we're going to work on the parallel connection between these two elements here. And then we are going to add this. And then the equivalent impedance is 20 in parallel with 5 is 4. 5 minus J, 4 minus J, 4 minus J ohms. All right? This is the equivalent impedance. Now, what we need to do is to calculate the open circuit voltage. To complete the Thevenin's equivalent circuit. Okay, the open circuit voltage would be to calculate the voltage here, VOC, when this is open. When this is open. If we open it, we calculate the VOC, and then the Thevenin's equivalent circuit would be VOC, which is a value in series with this equivalent impedance, and then the load here. All right? I just figured out that we don't need to worry about the open circuit voltage because the exercise wanted us merely to calculate the value of the load impedance for maximum power transfer. And I just got it. We will not need this. We simply say that Z is equal to 4 plus J. Okay? This is the response of this question. And why Z is 4 plus J? Because for maximum power transfer, the impedance of the load has to be the complex conjugate of the impedance of the circuit. Okay, my friends? This is all for question 14. Now let's go to the last question, question 15. Now let's go to the last question, question 15. In the following circuit, calculate the power in watts consumed by the 1 ohm resistor after the switch has been closed and steady state has been reached. Okay, my friends, this is the question. Let's go to the solution. After the steady state has been reached, the inductor is going to behave as a short circuit, and the capacitor is going to behave as an open circuit. Hence, the circuit behaves in steady state as we can reduce this circuit as this. The inductor behaves in steady state as a short circuit. And the capacitor behaves as an open circuit. Okay? No current is going to flow through the 3 ohms resistor because there is a short circuit here. Okay? This terminal here is in short circuit with this terminal here. This node, they make up the same node. So there is no current flowing here because there is no voltage drop. Do you understand? There is no voltage drop here from this point to this point. So there is no current here. The current is going to flow this way and will not pass in the 3 ohms resistor. And we have here 3 volts. And the value of the current is going to be 3 volts divided by 3 ohms. 1 plus 2 is 3. And it is 1 amp or 1 ampere. With the value of the current, we can calculate the power in watts. The power is 1 amp squared times the value of the resistance. This resistance here, and ultimately it is 1 watts. Okay, my friends, this is the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!